Well, one of the things we're going to emphasize in lab this week is that it's more complicated than I've kind of said. So I'm going to draw red circles around things that hopefully you recognize. You can hang your hats on the charges that those elements form. So red circles around the metals forming those cations, okay, and I'm going to do purple circles around the non-metals forming those anions, all right? All right. Now, that kind of leaves some other things. I'm going to draw some blue circles here. Do you see, like, for instance, Cr is chromium. It can form two different cations. Manganese, two different cations. And I just actually have a handful here, okay? These can form different cations, okay? And we're going to have to, how do I say, you will be able to deduce what cationic form that metal is, okay? Let's see, what else do I want to say? But I want to kind of pick on iron for a minute. So you're like, well, now why would iron form these two different cationic forms? So I'm going to pick on iron, and what you're going to see is actually it's going to be the valence electrons to go when it forms an Fe2 plus and an Fe3 plus. But the valence electrons are going to go, and it's going to lose it from the highest L first. So you're like, really? Do I need to remember that? Well, maybe. So L's, different types of L's, different types of, that's subshell types. We had our S, our P, our D, and our F, and remember there were values that went along with those. S's were 0, P's were 1, D's were 2, and F's were 3. So again, let's pick on iron without further ado. Iron actually has 26 protons, and if it's neutral, it's 26 electrons are configured this way. This is what you would get in order of using the arrow diagram. Okay, we kind of peter out with actually 6 electrons in the 3D subshell. But if I were to ask you what's the highest N, hopefully you would say the highest N is actually 4. So we only have, how many valence electrons do we have? We have 2 valence electrons in the 4s. So all that this did, and we kind of did an example of this, was to kind of rearrange this one in order of increasing N. So we have 2 valence electrons. So let's take a look at those two different cationic forms of iron. It can form an Fe2 plus where it loses 2 electrons. Well, that's pretty simple. Which 2 electrons do you think it will lose? Well, it will lose those 2 electrons in the 4s subshell. So here we are. This is how, the 20, instead of 26, it's 24 electrons. If we compare these 2 electron configurations, the only difference is that those 2 electrons are gone. And that formed a +2 cation. Well, let's take a look now at iron forming a +3 cation. So if it's a +3, that means what? 3 electrons have gone. And we know that it's going to be, these are the 2 of the 3, and I guess it's going to have to take 1 electron from the 3D, from the 3D subshell, and it does. So here we go. If we compare these, if we compare this one with this one, notice this is gone and one of these is gone. Okay? Instead of 3D5, instead of 3D6, it's 3D5. And do you see what happened here was, let's kind of pick on, between these two, we just need 1 more electron to go. Okay? And notice what our choices are. We have N is equal to 3. We have 3 different subshells we can choose from. But we have an L value of 0, an L value of 1, and an L value of 2. And the rule was it's going to go from the highest L value. So that's kind of where we see there. Now, actually, way back when we were talking about electron configurations, just in the previous unit, we said that actually having 5 electrons in any D-type subshell is kind of nice. Why? because D-type subshells have 5 orbitals. So it's kind of nice that we can just go ahead and for that Fe3 plus, this is kind of what we're looking at. I hope that helped. Oh, and on to just another problem slide. Just another problem slide.